What would you think if I told you that warp propulsion is no longer pure science fiction? Can you imagine that we will soon have spaceships traveling at the speed of light or even faster? Scientists have even discovered a completely new way to travel, 10 times faster than the speed of light. You'll be amazed at the fantastic changes this will bring in the future. Faster than sound, faster than light. Concorde, the supersonic passenger plane that took just 3.5 hours to fly from Paris to New York, was a milestone in aircraft development. Concorde has long been history. Today, only fighter jets fly at supersonic speeds. We humans have long since reached the next threshold. On our way into space, we need spaceships that are faster than light. Otherwise, the enormous distances in the cosmos cannot be bridged, and we would need millennia just to reach the next star system. For a long time, physics did not seem to allow humans or anything else made of matter to travel as fast as light. What was the reason for that? Well, it's simple. Einstein stated in his equations of general and special relativity that nothing in space can travel faster than light. Matter can't travel even close to that speed, because in that case, equations of dynamics and energy requirements no longer applied. Scientists truly had to think hard to solve this puzzle. Now, there may be a way to bend time and space to our will and create a spaceship that can travel faster than light. If you love science fiction space movies, you already know the warp drive from real life. The spaceship accelerates for a moment, then only a bright light can be seen and matter disappears in time and space to reappear at any place in the cosmos. Enormous distances are covered in a very short time, and travel to the farthest reaches of the cosmos would be real. Although the concept was popularized as pure entertainment by authors such as John W. Campbell and legendary Enterprise creator Gene Roddenberry, science picked up on the concept in the 1990s. Bypassing Einstein with a trick. Einstein's theory of special relativity states that energy and mass are interchangeable, and travel at the speed of light is impossible for material objects with a non-zero rest mass. This means that objects traveling at the speed of light require an infinite amount of kinetic energy to reach that speed. Theoretically, the dilemma can be solved by folding or warping space around the object. Warp means to distort or to bend. Instead of creating thrust with energy, the force is invested in distorting the space. A kind of fold is created, through which the spacecraft then slips with relatively little effort. Einstein's theories, which have become the scientific foundations of cosmology and physics, were unaffected by this concept. Two problems remained: generating the energy to fold space and technical feasibility. In 1994, Mexican physicist Miguel Alcubierre solved the problem at least at the theoretical level. He used Einstein's theory of general relativity during his doctoral studies at the University of Wales to develop a framework within the limits of the laws of physics that would allow faster-than-light travel. On the practical side, relativity states that objects become heavier and heavier as they travel faster and faster. It's logical. The heavier these objects become, the more difficult it becomes to maintain acceleration or even increase it to the point where a spacecraft reaches the speed of light. Only particles that have virtually no mass can travel at these enormous speeds. Photons are among them. Miguel Alcubierre developed a drive which was named after him. The principle is simple and easy to understand even for laymen. A purely local expansion of the space-time continuum behind the spacecraft and a contraction in front of it allows motion that is perceived as faster than light by observers outside the distorted region. The occupants in the distortion, on the other hand, would perceive nothing, or let's say not much. Perhaps they would perceive the famous tail of light, see the stars whizzing by, or notice a slight vibration. Within a few moments, a warped spaceship could cover immense distances truly as if in flight, or, otherwise said, in faster-than-light flight. The Alcubierre drive is virtually capable of expending an enormous amount of energy to contract and twist the space-time continuum in front of it, creating a bubble that simultaneously folds space. This bubble is a physical inertial system, which is why the occupants would not feel any actual acceleration. However, the rules of physics would be obeyed inside the bubble. Inside and outside, everything would conform, and nevertheless, matter could move in this way faster than light through space. only not with thrust and speed as we know it from cars, airplanes, or space probes, but by an ingenious trick. The universe offers unknown possibilities. One mistake we humans like to make is to think of the universe as one space. According to relativity, however, space-time is a flat sheet that is distorted by any object with mass. The space effect as we know it comes from the influence of mass, and it is this distortion of the space-time continuum found at all corners of the universe that we experience as gravity. Yes, even you are distorting space-time a little bit right now, as you are sitting there in front of your computer or smartphone, and you are causing gravity. In this context, of course, the exciting question arises whether a human being could also push through a time fold by consciously contracting the space in front of him and come out somewhere else in space. Theoretically, this is possible. Practically, however, you would have to produce a whole quantity of force in order to distort the space by a multiple more than this happens only by your weight. The Alcubierre drive creates the bubble, which is necessary to evade the laws of physics in the outside-inside with a propellant. This is exactly where we still have a bit of a problem, because whether we use diesel, gasoline, hydrogen, or methane, we currently can't muster the power. In fact, we would need energy equivalent to the mass of Jupiter to muster the energy with means known so far. In the meantime, however, a solution has been found for this problem. Negative matter. This exotic substance, which has a negative mass or energy density in theory, is supposed to be the long-sought answer. However, if we look a little more exactly, then we must find that here again a tiny little problem appears. Negative matter is not only hard to imagine, but also undiscovered so far. Its existence is suspected, but it is not proven. So how to construct a drive with something that may not even exist? And even if we could detect this form of matter, the question is, how could we collect or create enough of it to power a spaceship? Where there's a problem, there's a solution. Researchers don't rest easy when it comes to warp drive, because we need it, there's no question about it. Before we turn to the latest and most ingenious idea of a practically absolutely feasible warp drive, let's take another look at where we humans stand technically right now. Hold on tight, because now it could become painful for all who dream of faster-than-light travel. Our fastest spaceships. Speed of light is a universal physical constant that is approximately 300,000 kilometers per second. The fictional Enterprise could carry its heroes through space and to new adventures at maximum warp speed 9,000 times faster than the speed of light. Currently, our space probes are the fastest spacecraft we have. Probes are quite small and light. Nevertheless, they also need an immense amount of thrust to reach destinations such as Jupiter, Saturn, or Venus. The Juno probe, which orbited Jupiter from 1995 to 2003, traveled through space at a top speed of 74 kilometers per second, which is just 0.0002 times the speed of light. Voyager 1 took nearly 35 years to leave the solar system and is now more than 21 billion kilometers from Earth. The fastest spacecraft ever built by humans is the Parker Solar Probe, which reached up to 191 kilometers per second near the Sun. With these numbers, it's probably already clear to you that we humans do not make it very far with the technologies in the cosmos. For us, even small distances are great challenges. We could say in cosmic scales that we can just put our foot in front of the front door. Probes that scientists send into space usually use sophisticated acceleration maneuvers on the gravitational fields of planets to make any progress at all with a reasonable expenditure of energy. Some probes first orbit the Earth twice, then Venus, or they use Jupiter as an acceleration helper. On seemingly endless orbits, they slowly approach their destinations in the solar system over the course of several years. Imagine your buddy from the Proxima Centauri system invites you for coffee, and you would have to fly dozens of circles around some planets with your spaceship to get out of the solar system at all. And with the technologies available to us, probably nobody would arrive in time. Not even approximately. Because as it is at present, you would have to plan more than 100,000 years for a visit to the cosmic neighbor. Fact is, in such a way, we don't advance in the universe, and if we want to someday be a species which conquers space, new technologies must come. A realizable technology. The developments in the area of the warp technology go constantly further. Dr. Eric Lentz of the University of Göttingen recently presented a groundbreaking new approach to warp drive that bypasses the traditional problem of using negative matter and extremely large amounts of energy. In his study, Dr. Lentz describes how acceleration to the speed of light could be achieved using physical properties that already exist and can be implemented. The key lies in the use of so-called solitons, colloquially known as warp bubbles. This method only requires already known positive energy densities. Nevertheless, this technology still needs quite a bit of research in terms of its technical practicality. While people in Dresden were still thinking about this, the next groundbreaking announcement came. Dr. Harold Sonny White, a former NASA specialist, has discovered a real warp bubble. Although Dr. White was already researching the feasibility of a warp drive at NASA, he was actually working on something else entirely, and that was the Casimir cavity, which is observed between two metal plates placed extremely close to each other. Within this cavity exist tiny structures that are natural warp bubbles. The Defense Advanced Research Projects Agency is currently funding further research in this area. We basically just need to somehow mimic these small structures on a large scale and nicely, and the first true warp drive and possibilities for interstellar travel could be available. If tachyons really are what scientists think they are, they could mean a revolutionary change in our understanding of matter and energy. These particles are hypothetical particles that theoretically travel faster than light. It was Albert Einstein who showed in his theory of relativity that nothing can actually travel faster than light. If these particles now prove otherwise, they could be the passageway to a whole new dimension of the universe, taking us beyond relativity and its long-held field equations. They could even solve the riddle of dark matter once and for all, and thus explain one of the greatest mysteries of the universe. What are tachyons compared to light? Did you know that Einstein came to the conclusion that nothing can be faster than light? He realized that the speed of light is constant in a vacuum and remains independent of the motion of the observer. This assumption led him to formulate the principle of relativity, which states that the laws of physics are the same in all inertial frames of reference. From these considerations, he concluded that nothing can be faster than light, as this would lead to contradictions. In addition, his energy mass equivalence showed that infinite energy would be required to accelerate an object to the speed of light. These findings have so far been confirmed by numerous experiments. However, we may now be entering new physical territory where completely different laws apply. Tachyons not only exceed the speed of light, they theoretically even have a limitless speed, as they have no interaction with electromagnetic forces. Tachyon comes from the Greek word tachys, which means fast. The catch with these particles is that they are potentially unmeasurable. How could we measure something that presumably has no mass of its own and no speed that could be determined using conventional methods? The particle accelerator in Geneva shows us that such particles can exist. Here, researchers have already found a number of indications of particles that neither assume a stable form, nor are measurable in any way, nor have a mass. You would be amazed if you knew how many such particles there are. In the subatomic realm, it even appears that this type of building block of matter is much more common than any fixed, determinable quantity. In terms of our reality, this means nothing less than that our material world is not as solid, material, and predictable as we thought. Einstein didn't know everything? Albert Einstein, the great icon of astrophysics and astromathematics, put forward a famous theory of relativity around 100 years ago. For a long time, it was the extended basis of our Newtonian physics. But just as Newton could only describe part of nature and the cosmos in his era, Einstein also only recognized part of it. We can no longer avoid expanding these aspects of our natural science. The evidence that our old theories cannot be entirely correct can be seen everywhere. The James Webb Space Telescope is showing us rows and rows of discoveries that don't fit the old theories, and even Hubble, the old telescope, has shown us galaxies so old that they challenge the framework of our old physics at the time. It's no secret that the old calculations of researchers have long shown some serious weaknesses. In particular, our old formulas failed when it came to explaining the large-scale structures of the universe. Radio telescopes have discovered such gigantic structures in the universe that they span clusters of galaxies and never fit into the picture of objects that Einstein calculated. With our old approaches, we were also unable to explain the expansion of the universe, which is not linear everywhere and is also accelerating. Slowly, the clues are becoming abundantly clear, and it's very likely that the answer to the questions about the nature of our universe can be found in the world of the smallest particles. Where baryons, tachyons, quanta, quarks, and many others can be found, completely different conditions prevail. Particle physics breaks previous principles and challenges our physics due to its unpredictability. Tachyons, possibility of backwards time travel. What have scientists currently discovered? Researchers Samuel Kramer and Ian Redmount have found a possible explanation for the accelerated expansion of the universe in the data from Type 1a supernovae, and they have discovered even more. Tachyons could in fact finally explain to us the true nature of the mysterious dark matter. Dark matter makes up a large part of the universe and is one of the cornerstones of our cosmology. However, it remains completely invisible and unmeasurable to us. The magical thing about this type of matter is that it exists and has effects, but it does not interact directly with light or electromagnetic forces. Exactly the same is true for tachyons, which make them ideal candidates for dark matter. Their superluminal speeds could explain why dark matter is so difficult to detect and how it influences gravity to shape the motion of galaxies and the structure of the cosmos. So far, it's unclear whether tachyons are really direct building blocks of dark matter or whether they only exist within it. So the question remains as to what exactly these particles could be. Apart from dark matter, tachyons could have unique energetic properties that would be able to generate a completely new type of energy that is also difficult for us to describe or explain by conventional means. However, with such energies, we could, for example, master faster-than-light travel and possibly in the foreseeable future. Beyond this, tachyons could mean profound changes for quantum physics and subsequently change our entire understanding of the nature of matter and time. If tachyons actually exist and can transmit information faster than light, they could lead to scenarios in which cause and effect are reversed, challenging the principle of causality. The principle of causality basically states that every effect has a cause and that it precedes it in time, thereby establishing a certain sequence of events. The mere existence of tachyons would mean that information could be sent into the past, opening up intriguing, if paradoxical, possibilities and making the chain of causality suddenly appear illogical or elevating causality spatially and temporally to multiple dimensions simultaneously. This idea would fit in with another discovery. Researchers used a special research balloon at the South Pole to measure a mysterious stream of neutrinos coming directly from the Earth's interior. One of the few plausible explanations for the stream is a dimension hidden in the Earth's interior in which time actually runs backwards. So tachyons are far more than just an exciting and speculative idea that could explain dark matter. They have the potential to fundamentally overturn our understanding of reality. Unstable states in the quantum field and what they mean for our reality. Imagine particles moving faster than light as they appear in the quantum field. They're as crazy as they are, and despite their instability, they could interpret states that can transform the field in which they exist in a new, more stable state. It sounds paradoxical, but this could be the key to a universal understanding of the field equations. These particles are not just mathematical curiosities, they could actually act as catalysts for dramatic changes in the energetic state of a field. Imagine a field is in a metastable state, and tachyons could cause the field to fall to a lower energy state, potentially allowing for new physical phenomena and states. In quantum field theory, which describes the behavior of particles and fields in the subatomic range, tachyons are absolutely logical as mathematical solutions. The idea of tachyons even stems from the mathematical structure of quantum field theory. They showed physicists that their existence is almost absolutely necessary. This is why researchers first came up with the idea that tachyons could exist. However, these solutions are not uncontroversial, as they call into question the principles of special relativity, but quantum physics does that anyway. It is indisputably real, but absolutely incompatible with Albert Einstein's physics. Although Einstein himself was the first to discover a quantum and even received the Nobel Prize for it, he rejected quantum physics throughout his life due to its unpredictability. One example of the role of tachyons in quantum field theory is their function as unstable states. These unstable states, also known as tachyon condensation, can occur when a field is trapped in a metastable state. Due to the presence of tachyons, this field can transition to a more stable state through the principle of energetic minimum. This transition is similar to quanta striving for a state with the lowest possible energy. Tachyons serve as catalysts for such transitions. This would make them elementary building blocks of our reality at a low energy level. They could therefore be related to certain symmetries in physics. Symmetries are fundamental principles that describe the interplay of certain physical quantities under certain transformations. In this exciting context, tachyons could exist as particles that either preserve or break symmetry. Thus, these particles would be basic structures of many, if not all, physical systems and could provide us with the key to symmetry transformations and new insights into the structure of the universe. One particularly fascinating aspect of these symmetry considerations is supersymmetry, a theoretical extension of the standard model of particle physics. Supersymmetry postulates that every known particle has a supersymmetric partner. In this framework, tachyons could appear as supersymmetric partners of ordinary particles and play a crucial role in certain symmetry breaking. This symmetry breaking could reveal more and more new physical dimensions and phenomena that go far beyond our current theories. In quantum field theory and particle physics, symmetry breaking is a mechanism that can give rise to new physical states. If tachyons are involved in such symmetry breaking, they could fundamentally influence the dynamics and structure of fields and particles. This would not only mean that tachyons could explain how certain particle masses are generated, they could also help to understand reality more comprehensively, even manipulate it or create in our world what we previously thought was completely impossible. Faster than light. Light spreads out in tiny waves and at breakneck speed. If you switch on a light bulb in your home, the whole room is suddenly lit up. The time from switching it on until it reaches the state of full illumination is something you consciously don't notice. And you can't because it's less than a fraction of a microsecond. Light has some more interesting properties than just being fast. We know light as emission of the stars in the universe. The light is quasi-created as a byproduct of the stellar fusion processes. Quanta are also tiny particles of light and the building blocks of matter. Quantum physicists suggest that light is one of the main carriers of information in the cosmos. The fact that light is a quantity in the universe was determined by Albert Einstein scarcely 100 years ago. He found out that light, or its speed, is the only constant and not relative force in the universe. The speed of light moving through a vacuum is about 186,282 feet per second. Another cosmic unit of measurement for light is the light year. This indicates the distance that light can travel in the cosmos in 1 year. This value is about 6.2 billion miles. The light year is a unit of measurement used by astronomers and physicists to measure and describe the vast distances in our universe. If humans wanted to travel to Mars, they would need, depending upon the position of Earth and Mars, at the present moment, 5 months to 2 years. If humans wanted to travel under the present circumstances to the end of the solar system, they would be more than 100 years on the way. The comparatively small Voyager probe needs 33 years for this journey to the nearest Alpha Centauri star system, 4.3 light-years away. A large spacecraft would need several thousand years. If we look at these distances realistically, we must admit that we humans still have some work to do if we want to travel through space or even within our own solar system. The dream of manned space travel. Manned spaceflight has been virtually non-existent since the lunar missions. From the 1960s to 80s, NASA sent humans to the moon, At present, humans stay in the cosmos in the space station ISS, close to Earth. But that's it. So far, we have not gone further than the moon, and that was 40 years ago. NASA and the new space pioneers SpaceX and Blue Origin would like to send humans into space again in the foreseeable future. Blue Origin, the spaceflight company of Amazon CEO Jeff Bezos, and Elon Musk's SpaceX are planning manned flights to the moon. SpaceX even wants to send the first scientists to Mars starting in the 2030s. The big problem with these trips remains the distances, time, and stresses placed on the human body during flights in space. Already, astronauts are only allowed to stay on the ISS for 6 months. Otherwise, they face problems such as muscle atrophy, eye damage, and an increased risk of cancer from high levels of cosmic radiation. Spacecraft traveling at close to the speed of light could reduce the travel time from Earth to Mars to a few minutes. Traveling in a warp bubble would largely spare humans from cosmic rays and other harmful effects of interstellar space flight. Before we get to the point where humans fly with superluminal speeds by manipulations of space-time, we'd need spaceships 2 or 3 times faster than the present ones, an enormous leap in technology. Elon Musk is the first man who wants to send humans to Mars. The announcements of Mars missions and construction plans for a Mars colony have been known for years, yet recognized physicists and astronomers currently still doubt that projects like these will be realistically feasible unless we have faster spaceships available. In 2019, noted U.S. astrophysicist Neil deGrasse Tyson challenged the SpaceX and Tesla CEO via Twitter. deGrasse Tyson urged the multi-billionaire to stop spending time and money on cyber trucks, Hyperloops, or Mars rockets. Rather, Musk should look into developing a warp drive. Musk countered at the time that his planned city on Mars will be the powerful driving force to invent warp drive. Exactly what Musk meant by that remains unanswered to this day. No one currently knows whether SpaceX is cooperating with international scientists and working on warp drive or not. How realistic is the warp drive? Up to now, experts have argued whether and how the legendary drive we all know from Star Trek and other science fiction movies will be realizable. As early as the early 1990s, physicists were testing the idea. At first, the prospects were bleak, but as early as 1994, a Mexican researcher presented a calculation according to which the fantastic drive would actually be feasible. As a quick reminder, warp drive sends spaceships through space by compressing space in front of the spaceship and expanding it behind the vehicle. This creates manipulation folds in the space-time fabric over which further distances can be covered in the blink of an eye. In 1994, Miguel Alcubierre became the first person to prove that propulsion did not violate Einstein's laws, as previously believed. The only problem with Alcubierre's solution was the relatively large amount of energy needed to manipulate space-time. Without gigantic reactors on board, his spaceship would not have been able to get off the ground any faster than it did today. But a solution was soon found to this problem as well. In 2010, the US researcher Dr. Harold G. Sonny White found a type of propulsion that requires no fuel or energy at all, and only so-called negative or exotic energy. The new problem that arose was the fact that the existence of negative matter had not been proven in 2010. That changed in 2021. White was able to demonstrate the presence of small amounts of negative matter in the Casimir effect. So far, this is not enough to power a spaceship weighing tons, but the technology could hold promise for the future. This is far from the end of the innovations surrounding warp drive and flying at the speed of light. The EM Drive, microwave drive. Before the existence of negative matter could be proven, researchers primarily set out to develop models of super-fast motion that do not require energy. The most promising concept came from a British scientist named Roger Scheuer, a former project manager for the Astrium Space Company. He has developed a hypothetical microwave drive that could rival warp drive. Scheuer's EM Drive theoretically works by trapping microwaves in a kind of copper cone and creating thrust by bouncing them off. The EM Drive relies primarily on Newton's second law, which defines force as the rate of change of momentum. The electromagnetic wave propagating at the speed of light has a certain momentum which, when transferred to a reflector, results in a tiny force. Accumulated accordingly, the tiny amount could become such a large force that the EM drive, without any propellant at all, might not be able to reach the speed of light, but it would be a significant improvement. NASA announced that tests with an engine based on EM technology had been successful several times. Shortly afterwards, a scientific group from China announced that it had also successfully tested this engine. Tested in Dresden and found to be unsuitable. Critical scientists did not readily believe the results of NASA and the Chinese. Ideas about microwaves generating thrusts sounded too unreal, and some German physicists raised questions such as how these waves should be initiated, how they should move, and where they should get their momentum. Consequently, they were put to the test. The test took place at the Technical University of Dresden. In Dresden, they came to quite different results, and the researchers told NASA and their Chinese colleagues that something could not have been quite right with their test series, because in Dresden, the EM drive failed despite several attempts. Since NASA did not comment further on these criticisms and no statement could be heard from China either, all hopes have turned back to the warp drive. After all, once implemented, it could solve almost all the problems of manned spaceflight in one fell swoop. In an artificially generated warp bubble, it's not the spaceship that moves, but the universe, so to speak. In the best case, the occupants of a warp spacecraft would not notice much of their interstellar journey. Will Dr. Eric Lentz bring us warp drive? When Captain Picard was jetting through space and time on the Enterprise, physicist Eric Lentz, now 34, was still a young boy. Even then, Lentz couldn't stop wondering whether warp drive was realistically possible. During the pandemic, Lentz, who had almost lost his job, took another look at the Alcubierre drive and Dr. White's improvement out of boredom, looking for a solution to the energy problem. Due to a special circumstance in the geometry of space-time, Lentz found solutions for the drive that did not require the use of exotic or negative energy at all. He discovered the solution in Einstein's field equations. Thanks to these, one can calculate how certain matter and energy distributions distort space-time. Like Alcubierre, Lentz decomposed space-time into stacked layers for this purpose. Only the practical astrophysicist Lentz searched for much more complex units than the theoretical physicist Alcubierre and found them. Lentz's draft provides for the use of a large quantity of energy, for it consistently uses positive forces whose existence is already known, confirmed, and available. Positive energy is a concept that goes back to the Swiss research group Applied Physics, another group that presented the concept of a superfast propulsion without fuel. Although the model does not go beyond the speed of light, it could realistically advance space travel enormously in just a few years. You probably know that light is very fast. It travels at an incredible speed of about 299,792,458 meters per second. And nothing we know of travels faster than light. When the spaceship accelerates to high speeds, the light coming from the stars is initially affected in a very special way. The stars would behave differently depending on whether your spaceship is traveling towards them or away from them. The light from the stars you are moving away from would be shifted towards the red end of the light spectrum, which is called a redshift. This redshift occurs because the spaceship is moving away from the star's light, shifting the light into longer wavelengths and the corresponding red hues. The stars behind you would therefore become increasingly blurred and red. The light of the stars you are racing towards, on the other hand, would be shifted towards the blue color spectrum. This happens because your spaceship is moving towards the light of the star, which shifts the light to shorter wavelengths. In physics, this is called the Doppler effect, and in practice, astronomers use this effect to determine the speed and distance of stars and galaxies in the universe. There are no stars. Let's move on to another exciting phenomenon of your space journey. The Doppler effect is not quite right. If you were sitting in your spaceship and looking outside, you probably wouldn't see any stars at all. And there's a simple reason for that. All astronauts who have been to the cosmos or the moon have reported that there are no stars in the universe. We usually think that the starry sky in space should be much brighter and more beautiful than here on Earth, and then you are in the universe and the stars are gone. There are two reasons for this effect. In the weightlessness of space, You are floating in a vacuum with no atmosphere or air to scatter the sunlight. On Earth, the atmosphere scatters the light from the sun and stars, making the sky appear blue during the day and dotted with stars at night. But in space, far away from Earth, there is no such scattering of light. This means that the light from the stars reaches you directly from the stars without being scattered. This may sound great at first, but there is a catch. The light from the stars is very weak, and if you are close to the sun, our sun would intensify this effect. Your eyes wouldn't be able to see what little light there is, and the sunlight is so bright that it outshines the faint starlight. Scientists suspect that this effect would even occur when traveling between star systems. Again, it would be the vacuum of space that prevents the light from the stars from being scattered. Only when you get closer to the next star system and the particle density increases, would you see light again. This is strange, isn't it? Because we know from movies and television depictions in which the universe is full of bright stars as seen from spaceships. On your journey through space, however, you would encounter even more strange things that you certainly didn't expect. You are young, and everyone else has aged. You may think that time is the same all over the world, but that's not necessarily true. According to Einstein's special theory of relativity, time slows down when you move at a high speed. This means that if you take a long journey through space at high speed, time will pass more slowly in your spaceship than for people on Earth. That really sounds like something out of a science fiction movie, doesn't it? Assuming you fly through space at very high speed for 3 years and then return to Earth, it would feel to you as if only 3 years had passed. You would have aged 3 years in that time, and you would remember the travel time of 3 years. But here's the fascinating part. According to Einstein's laws, more time has passed during your space travel. So you would come back to a world where friends and family have aged much more than you have, and for these people, much more has happened. This phenomenon is called time dilation, and it shows how strange and fascinating time can be in different situations in the universe. Time is a quantity of physics that still poses some mysteries. We do not know how it behaves in the other parts of the universe and whether there are ways to circumvent or control it. Timeless travel with the warp drive. Einstein's laws have even more pitfalls because nothing can actually travel faster than light. No matter with a rest mass can even come close to the speed of light. Whether we will ever be able to travel at the speed of light is therefore questionable, but we may be able to travel much faster and easier with a trick. Researchers have adopted the idea of warping space from science fiction literature. The spaceship does not move through space, but rather bends space and itself a little and then slips through a hole in the space-time structure, and you would be anywhere in the universe in a flash. Sounds crazy, but we won't be able to manage interstellar travel any other way. Because even at the speed of light, it would still take us more than 3 years to get to the next star system, Alpha Centauri. So if we want to explore space, we need faster than light speed or the warp trick. What you would see on board a warp spaceship when it slips through folded space-time is a mystery. Nobody can imagine it yet. You would probably only see darkness until the light of the targeted star system came into range. What happens to the body? We take a short journey back in time to the year 2150. Unfortunately, warp drive has not yet been achieved, but thanks to the revolutionary technologies and the discovery of a new energy source material, spaceships capable of reaching the speed of light have been developed. The first crew to travel at the speed of light consisted of 5 astronauts who embarked on a mission to explore a distant solar system. However, they soon realized that this type of journey had some effects on their bodies. The journey began innocently enough. As the spaceship accelerated to reach the speed of light, the crew felt as if they were sinking into a deep sleep, even though they were awake. This was a kind of side effect of the flight, and the sleep was also intended to protect the crew from the psychological stress of the extreme speed. Once they reached the speed of light, the physical effects began to show. The astronauts noticed that their bodies were shrinking, as if they were suddenly getting younger. This was due to time dilation, which we have already looked at. The gravitational forces acting on the crew during the flight were also not without consequences. With constant acceleration, the astronauts were pressed more and more onto the floor of their spaceship as their speed increased. This led to muscular atrophy and bone loss. As the journey progressed, The astronauts found it difficult to tell the time as their clocks were running faster and faster compared to time on Earth. They could not be sure how long they had been traveling or how long they had been absent on Earth. The crew became completely disoriented, but luckily the spaceship was flying with automatic controls. Eventually, the crew reached their destination, a distant solar system, and assuming these 5 brave space travelers survived the ordeal, they made some amazing scientific discoveries at their destination. When they returned to Earth, after another ordeal of faster-than-light space travel, they realized that many decades had passed, while only a few years had passed for them. This clearly shows that the matter of the speed of light will very probably not work out with regard to our bodies either. But what other options do we have for traveling through space? When will we be able to teleport? The idea that humans could use teleportation to travel through space is another fascinating concept that often appears in science fiction. There, the process is usually called beaming. When matter is teleported, it is disintegrated, transported to another location, and reassembled there. However, there are some major challenges and physical laws that make such ideas difficult. Theoretically, an object made of matter can be reduced to its information. The evidence for this has already been provided by quantum mechanics. Based on the information, the object could theoretically be reconstructed at a different location. However, the greatest challenge on a purely mathematical level is the exact replication of a human being or a spaceship on an atomic level in order to recreate it in another location. This requires an incredible amount of data and the ability to capture the entire complex structure of a human being and reconstruct it in another location. Of course, there are still some aspects of biology that speak against this. What happens to the matter, the blood, the organs, and above all, how is all this recreated at the destination? We are reconstructing a UFO. If we believe the many thousands of UFO sightings that have been reported in the last 100 years alone, these flying objects have long since transcended the laws of physics as we know them. They move in a way that contradicts the laws of Newtonian physics, dynamics, and acceleration. Pilots report flying saucers that navigate in a crisscross and very quickly through space, while others can allegedly take off almost vertically from the ground. Light speed, fiction, and reality. Iconic science fiction movies like the legendary Star Wars series show how it could work. As soon as Han Solo ventures into hyperspace with his Millennium Falcon and subsequently travels at a multiple of the speed of light, the fictional character leaves millions of miles behind him within the blink of an eye, and then arrives safely and unharmed at the desired destination. Now, we know that pop cultural machinations of this kind are not necessarily suitable for providing a scientifically sound picture of the actual conditions in space. For example, many of you are probably aware that the fast-paced space battles on the big screen would in fact be accompanied by an oppressive silence and not by bombastic soundscapes. In fact, sound cannot propagate in space as it does on our home planet, since the yawning emptiness there simply means that sound lacks the necessary physical guiding medium. According to Albert Einstein's theory of relativity, there is a fixed speed limit that cannot be exceeded, the speed of light. As the name of this unit of measurement indicates, it's a value that refers to the speed that light rays reach in a vacuum. Specifically, the speed of light amounts to an incredible 186,000 miles per second. As a reminder, a jumbo jet, which actually seems to us to be an incomparably fast means of transport, reaches a maximum speed of just 0.15 miles per second. In astronomical research, the speed of light is an important parameter that experts use to determine the exact distances between objects in space. It's a unit of measurement long established among experts. Scientists also use the distance that light can travel within a year. The corresponding distance is an incredible 5.9 trillion miles. If the aforementioned jumbo jet were to attempt to bridge the corresponding distance, it would need no less than 1.2 million years to do so. The attempt to accelerate a solid object to the speed of light, however, turns out to be a practically impossible undertaking. In fact, only massless particles and electromagnetic radiation can travel at the speed of light. But why is that? Why we cannot travel at the speed of light? To answer this question, we must draw upon relativity theory again. According to this theory, the mass of an object is always directly related to the speed at which it moves through space. It doesn't matter at all whether it is a tiny elementary particle or a huge airplane, since the mass of an object is always dependent on its speed. This means in the reverse conclusion that mass becomes ever larger the more the speed of the object increases. The energy required to accelerate an object is also directly related to the mass of the body. The heavier a structure is, the more energy must be used to increase its speed. This constantly increasing energy requirement, which would be necessary to accelerate a massive structure to the speed of light, can simply not be guaranteed. If a passenger airplane were to reach about 75% of the speed of light, it would already possess 1.5 times its original mass due to the law of physics. At 99% of the speed, it would already be 7 times heavier than before. The further one approaches the targeted speed of light, the more rapid would be the increase in the energy required to continue accelerating the object. In other words, this would mean that the corresponding energy demand would practically converge towards infinity when reaching the speed of light. Thus, it would formally take infinite energy to propel a physical entity at the speed of light, and providing the required energy on an infinite scale is simply impossible. Approaching the speed of light. Let us now assume that we at least succeeded in building a spaceship that reaches 90% of the speed of light. This circumstance would entail in theory some amazing concomitants. According to this, time for the person in the spaceship would pass perceptibly more slowly than for someone not traveling through space at the speed of light. In this case, the person traveling at the speed of light would experience a period of 10 minutes, while the corresponding value for a person not moving at that speed would be 20 minutes. Time would be shortened for the space traveler in this case by half. In addition, the field of vision for the astronaut would change drastically. What he would see during his flight would be a tunnel-shaped window in front of the cockpit of his spaceship, in which the surrounding stars would pass by in glistening red and blue tones. The reason for this is that the light waves of the celestial bodies in front of the astronaut would be optically compressed due to the intense speed of the spaceship. This circumstance would make the objects appear blue. The light waves of those stars spread out behind the spacecraft would present themselves in a red color due to the Doppler effect. As soon as a certain speed limit was exceeded, the light waves would finally lie outside the visible spectrum, at which point nothing but a vast blackness would present itself to the observer. In addition to these breathtaking circumstances, however, the potential approach to the speed of light also entails some serious risks. The faster we moved, the more dangerous would be the small space particles that collided with the spacecraft during such a rapid maneuver. These would quickly become threatening projectiles that could bring the theoretical flight to an abrupt end. Should it be possible one day to bring the speed of a projectile closer to the speed of light, the construction of special protective shields would be indispensable. Further problems. Let's imagine that mankind actually succeeded in constructing a spaceship that would approach the speed of light to a fabulous 99.9%. Renowned space agencies might then strive to reach the world-famous double-star system Alpha Centauri. As is known, these celestial bodies are located in the constellation of the Centaur, a good 4 light-years away from our blue home planet. With the speed of the spaceship approximating the speed of light, it would thus take approximately 4 years before the astronauts reaching the goal point of their galactic journey. A person moving over a period of 4 years at the approximate speed of light experiences a subjective span of just 14 days, due to the associated time dilation. In other words, the fact that the faster an object moves in space, the slower time passes. On Earth, not 14 days, but a full 4 years would pass. Provided that the means of communication of the future would allow it, the exchange of information between the astronaut crew and the earthly facilities would be subject to extreme delays. In fact, a message transmitted from Alpha Centauri would also take 4 years before finally reach the communication centers on Earth. The future of propulsion technologies. While the example just presented is still a purely fictitious idea, the question remains open as to how the propulsion technologies of spaceships will develop in reality. This is also the topic that physicist Philip Lubin has been devoting himself to for several years. Together with his colleagues at the University of California, the scientist is looking for new ways to rapidly accelerate future space projects. The researchers believe that the key to this lies in photon propulsion. The corresponding spacecraft should be propelled by an incomparably powerful laser for practically the entire flight. Very light space probes could reach 25% of the speed of light with this technology. The corresponding speed would therefore be about 47,000 miles per second. By way of comparison, New Horizons once left our planet at a speed of just about 10 miles per second. However, the larger the spacecraft, the lower the maximum speed that could be generated with the help of photon propulsion. Nevertheless, large manned ships would still have a remarkable speed of 621 miles per second. In the case of the previously mentioned star system Alpha Centauri, an unmanned space probe would need about 20 years for its flight. In fact, the mode of operation of a laser propulsion system differs significantly from the systems currently in use, which rely on the recoil principle. The rockets generate their thrust by burning fuel and emitting gases that accelerate the spacecraft. A photon drive, meanwhile, would involve several powerful lasers circling our home planet. These would then be aligned with the corresponding spacecraft. This spacecraft would be equipped with a gigantic sail, which would reflect most of the incoming laser light. The photons would meanwhile transfer an impulse to the sail construction and thus accelerate it. However, it will probably be many years before this futuristic concept can actually be put into practice. Actually simple, right? The big question of this video, whether time stops when reaching the speed of light, can be explained with this simple sentence. On the level of light, there is no time at all. For a light particle, or in other words, a photon, which apparently travels through space with the speed of light, no time passes. The impression of time arises only on the level of the observers, or in other words, we humans. That space and time are illusions of the mind is a claim not only mystical schools make, but also the great physicist Albert Einstein, who came to the conclusion that the universe is not in truth what we think we see. In all his observations, time actually turned out to be one of the strangest quantities that we know of, even though we usually live with it in everyday life without giving it too much thought. The relativity of time. Let's now take a closer look at these theses. When light has traveled 1 light second, this second has passed only in the perception of the observers. From the point of view of the photon, no time passes. Basically, the particle does not even cover a distance through space. On light level, the whole space it crosses is shrunk essentially to zero. Now the exciting question is whether we humans can also experience a standstill of time when we reach light speed in a vehicle like a spaceship. Theoretically, yes, but practically, there are 2 hurdles here. First, we would have to achieve an acceleration of 186,000 miles per second. If we were then traveling at the speed of light, time would also stand still for us in the spaceship compared to the surrounding matter. The fact that it does not come to a complete standstill is simply due to the fact that a spaceship and a human body can never completely reach the properties of light despite the speed of light. Forces like the rest mass of matter, resistances, etc. remain. The second problem is that it's currently impossible to accelerate matter to the speed of light without consuming an amount of energy that approaches infinity. In plain language, this means reaching the speed of light is not possible using classical physical quantities and mechanical drives. However, this does not mean that humans will never travel at the speed of light or even faster. Scientists are currently researching ways to bend space-time and use negative or exotic matter to achieve acceleration by manipulating forces. Does light really have a speed then? At the photon level, time stops from our point of view. We cannot tell how a photon experiences time, or if it experiences anything at all. Einstein found out about 100 years ago that the speed of light is the only constant and not relative quantity in space. However, the behavior of light in its smallest particles is again anything but constant. An important aspect of velocity measurement is also a relative. and not a constant quantity, time. Velocities indicate the distance that something, in this case a light particle, travels within a certain time in a measurable space. But also, space could be not as linear as we imagine it on Earth, and the calculations of physicists must always start from an edge of space. With respect to space, we don't even know yet if these boundaries exist. If you follow our videos often or subscribe to our channel, you probably know that the latest findings of the James Webb Space Telescope have found that previous theories of distance measurement based on light shifts in space are currently under scrutiny. Either there were mistakes here, or with the Big Bang Theory, or there really are galaxies which should not exist at all. On Earth, experiments showed that light spreads with a certain speed. However, at present, we know too little about the real nature and origin of the cosmos to know for sure if the observations on Earth also apply to every corner of space. If light has to pass through thin forms of matter, it slows down minimally. So we can't exclude that the speed of light behaves differently somewhere in space, even if Einstein thought that the speed of light is an irrefutable constant. Quantum physics and photons are nothing more than quanta, prove that light is not constant in the microcosm of the small particles. Rather, it seems to be physically neither at a certain place nor at a certain time. This could support theories that the impression of motion, space, and time exists only in our perception. According to the latest findings, space could also be something like a gigantic holographic projection. What exactly the connections between the level of light and the material world are, researchers do not know at present. Just how crazily time behaves and why it stops when humans reach light speed, we'll show you now. The phenomenon of time dilation. For the following thought experiment, we need a simple reference frame for time. Suppose a photon bounces between two horizontal mirrors. Since the speed of light is a universal constant, the time that elapses between two bounces is always constant. In this case, one bounce is 1 unit of time. Now we transfer the picture to an everyday scene. We imagine a person who goes to his lunch break and drinks a coffee and eats a roll. His break lasts 100 time units. At the same time, NASA astronauts are happily testing a spacecraft that has already reached half the speed of light. The man as well as the astronauts of NASA have a clock which corresponds to our photon clock, and thus the same length of time interval. The astronauts do not have the feeling of moving on their flight. They sit in their chairs, and only when they see the world passing by would they have a sense of movement. From this point of view, the man on his lunch break would race past the resting astronauts at half the speed of light. Thereby, he sits quietly at a table in the cafe. From the point of view of relativity, physics, and time, it's impossible to say which of the two views is the correct one. The time shift we are about to show you is real for the astronauts, even if in reality, the man is not moving at half the speed of light. The photon clock of the man in the cafe would also move with half the speed of light as seen from the spaceship. By the angle which then arises from the perspective of the spaceship and the speed, the photon would cover a much longer way between the two bounce intervals. So the time unit on the photon clock of the man is then further apart. Since the astronauts aboard the spaceship can only observe the events with their own photon clock, the time units would still match the initial image. The photon is moving up and down, and the amount of time it takes for this movement has remained the same. Since the speed of light is the same in each reference frame, the distance the photon travels in both clocks is theoretically the same. Nevertheless, the astronaut's clock ticks faster than that of the man in the cafe. If the man finished his lunch break after 100 time units, much more time units would have passed for the astronauts, because the photon on their clock had to travel the direct way and not the way via the extended angle. On the photon clock of the astronauts, 120 time units could have passed. This phenomenon is called time dilation in physics. If a person moves past an observer, it can be observed that the clock of this person ticks much slower than that of the observer. We can also illuminate this effect a little more deeply. People are made of matter, which basically consists of charged particles called electrons and quarks. The particles form matter, in which they exert a force, and this comes about in the exchange of photons. We know this effect as electromagnetism. This force is not only behind the formation of elements in matter, but also behind all kinds of movement or life. Breathing, thinking, eating, and metabolism have to do with these forces. During all these actions, photons are in motion, which means they travel distances so that interactions, motion and force, can take place. As the man in the cafe moves past the astronauts at tremendous speed, not only do the photons in his clock take longer to tick, but so do the photons in the electromagnetic interactions of his body. Viewed from the spacecraft, the man's hand would move more slowly to his mouth at lunchtime, his heartbeat would be slowed, and even cell division would proceed differently. If the speed of the spaceship increases to the speed of light, this time delay would be so great that the man's heartbeat and breathing would come to a virtual standstill on Earth. Time and the sequence of events would be suspended. Meanwhile, not much changes for the man on Earth. His heart would continue to beat normally, and the next day, he would again be sitting at his lunch break for exactly 100 time units. From the perspective of the spacecraft, however, this phenomenon means that the man on Earth would age more slowly than the astronauts. Research continues. Currently, scientists are still not sure how the phenomenon of time dilation would affect astronauts on long space flights, or perhaps we have not yet properly understood the dimension of time. Among other things, scientists are currently working on slowing down light to the point where it no longer travels at the speed of light. At Imperial College in London, this is said to have already been achieved. Light was slowed down by a factor of 15 million and then only traveled at 66 feet per second. But if we now remember that light itself probably knows neither time nor space, and if we succeed in slowing light down to such an extent that it virtually matches our speed, we might be able to build light gates that allow us to travel through time and space. Exciting, isn't it? Now tell us what you think of the fascination of light and its possibilities. Do you also think that light could be the key to the universe, or at least to travel within the cosmos? We look forward to your contributions to the topic in the comments, and thanks for watching.